Today we will be discussing on another interesting aspect for any microprocessor system, which is the timers. So we already covered on the interfacing part, we already covered GPIOs, then we discussed in detail about interrupts. And now this is another important aspect. We cannot call it as an interface, it is a peripheral definitely. And timers are very important, right? So let's deep dive into timers. So if you see why there is a requirement of timers, you can treat your mobile phone as a microprocessor system. You have all these options you might have seen in the mobile phone. A clock, which is a sort of a measure of the time for us, right? So no explanation required on that. Alarm is our friend most of the time to wake up. Is a timer as well as it is an interrupt, right? Interesting. So we already discussed the importance of that in the previous lecture. A stopwatch extremely important for us to give a measure of some work that we are doing, how much time it took, for example. And then a timer can run as a free running clock. Is something like inverted clock, I would say. Is something like you set a time and then ask the timer to count down to 0, and you want to do something within that time interval, something like a competition. So these sort of us sort of inverted, but here it's more of a stringent timeline measurement. Moving on, in the case of a microprocessor system, typically the timers, so these are the functional description of timers. Technical description of timers, I would say in this way: a free run counter. This is basically some or a down counter which just runs to some value or from some value to 0. There are many purposes for it, obviously. One of them is like you want to see whether your work is done within a certain time interval. Other functions include input capture, which is typically employed for polling. So you want to measure and input at certain intervals of time. So you put a timer, and every time that timer counts to a certain value, or every time a counter counts from a certain value to 0, you poll the input. Okay, you see what is the input value. So polling, I don't know whether you thought about it in the previous lecture. How are you going to do polling? Is exactly like this. You set a timer, and at the end of the timer you poll the input. Okay, so that's the way we are doing. That's an application for input capture mode. We'll explain in detail each one of these, how it is done in a circuit level. Then output compare, extremely useful. So for example, something like a PWM, the pulse width modulation generation, extremely useful. So let's go into deep dive mode into each of these aspects. So we'll start with the general overall architecture. So this is another way to look at your microprocessor system. Introduce another one way to look at it in the previous lecture. This is another way. Don't get confused. Everything is same, only the layout and different ways and different people present in different way. One of the textbooks. So this is a different way to look at it. Again, I just want to highlight here. So this is the software level that you will be communicating with, and their thing below the dotted line to this dotted line is within the microprocessor. Outside of this is where your interface things will come. So you have the processor CPU core here. There is an interrupt thing which is going to the NVIC in the previous slide. If you go and see, the nested vector interrupt controller sits here and then communicates to CPU. The software exceptions or the hardware exceptions will come directly to the CPU. It won't pass through the NVIC as we discussed last time. And then going to this side, of course, the interrupt channel is different. It will communicate through the NVIC to the CPU. Anything other than that, the typical load store operation will communicate through the bus, right? The system bus. Each of these GPIO, timers, USRT, which includes I2C, CSPI, and your serial protocol basically. DAC, ADC, external, internal memory, everything will communicate to CPU in the conventional way through the bus system. If it is interrupt based, it will have to go through the NVIC. So that concept should go into your mind. Okay. So let's move on. Today we are going to talk about timers. We already completed GPIO, and I briefly explained we can configure port A and port D of our Freedom board as an interrupt as well. And you can try it out. You're free to do it actually. It's quite easy. The basic things I already explained, you just follow those and then try to do yourself when you get the board in your hand. Okay. And timers is what you're going to deal with today. So two typical modes are available, compare and capture, and the other mode is of course the free running mode. So we'll explain in detail in the next few slides what each one of them means. Okay. And the remaining classes actually nicely put up here. So remaining classes, one session will be on, or maybe 1 or 2 sessions will be dedicated to the serial protocol. Each one of these, UART, SPI, I2C. And you have experiment in the lab on UART alone, but that doesn't prevent you to try out I2C and SPI on your own. Okay. Then we have another session on DAC, ADC, and with an experiment on them as well. And then a short, crisp, brief session on the memory interface, because memory typically comes to the advanced level where something like a direct memory access is extremely useful. We'll briefly touch upon it, but if somebody is interested, I encourage them to do the advanced course on microprocessors, where they will help, where they will understand that. So in this lecture, let's focus on the timers, and this is a brief introduction of that. The slides look vague to you, but don't worry, it's very simple. So let me go very, very slowly here. So you have the external interface here, and there is a provision to actually give an external clock. So external oscillator you can connect, and then you can give your own clock. That is important because that is a, or you can select the internal clock also, which is restricted, which is predefined, and you don't have any variation from there. Of course, you can pre-scale it. Moment you have a certain clock frequency, you can actually scale that clock frequency, typically reduce that clock frequency, and that provision is there. We'll go in detail about that in the subsequent slides. The 3 operations possible, one is the free running mode, the other one is a compare operation, and the other one is a capture operation. We'll explain these 3 in detail in the later. That forms the hardware part. When I say hardware, it is a digital logic essentially doing a function for you. It can be a simple counting, it can be a comparison operation, a comparator, or it can be a capture operation. So we'll discuss that in detail later. On the software side, as usual, as a programmer, you have access to certain registers, certain memory locations where you need to write some things so that you configure it as a free running counter, or configure it as a compare operation to generate a PWM output, or configure it as a capture to capture certain input, maybe a polling operation. Okay? And then of course, you can go to an operating system level where you write codes in C++, where you call some of these assembly abstractions to write it in a much easier way. I have a separate extra session on C coding aspect, which is not very mandatory for you. Those who like that could actually see that video, maybe towards the end. Okay. And then of course the application software that you build upon, maybe something like you on an LED based on the temperature, something like that. I'm just telling an example. Moving on, let's now have a deep dive into these 3 aspects. Okay. So this is a brief description of each of these individual things that I listed in this slide. So I already explained, or will explain in detail in the next subsequent slides. So we'll not read out it here. It's up to you to read it out and understand. Okay. Moving on, so this is the first aspect, the free running clock aspect of it. So this is sort of the engineering viewpoint. So you have an external or an internal clock which produces a certain clock frequency. Let's call it as F clock. That is going to a pre-scaler. So this pre-scaler, what it essentially does is it scales down the frequency. So you can safely say you don't want to scale the frequency, then you can put a 0 value. And then the output is given by F clock pre-scaled. So the relation between F clock pre-scaled to F clock is something like this. You can clearly notice this is scaling down the F clock because PSC value can take values from 0 upwards. And we are added a 1 here. The reason for it is if 1 is not there, you put a 0 value here, this will go for a stack overflow, right? So that's not possible. So 0, you put it here. 0 plus 1 is 1. So F clock by 1 is F clock. So that means your frequency is not scaled. That's what you want by putting 0. So there is no 1 here. If you put 1, you effectively get F clock by 2. That means That's correct, right? Because you can only scale typically by an integer value. Otherwise, it's a complex circuitry. So you scale by 1, which is nothing but MOS scaling. You scale by 2, you scale by, so you put 3 here or 2 here, it will be scaled by 3, but most probably it will round up or round down. Okay. So some prescale value that you give, it will only, so if you go back to the previous slide, I have written it here. So the scalar is only possible in these aspects for 816. So it's 2 for 816, I would say. So it's mostly integer values or 2 to the power of values. I should not say integer values, 2 to the power of values, because that's easier to. And then you have a timer counter, and that counter you can load some value. So this counter you have the provision to count it up or count it down. There is a register where you have to write to that register that determines whether this will act as an up counter or it will act as a down counter. Initial value from where you want to start the counting in the case of a down counter, or the value to which you want to count up, can be loaded. This is a user control register. Again, you load the value here. That value will be the value to which the counter will count up to or count down. Okay, count down from rather. So let's assume this is a down counter, and then what it happens is, if the down counter is 0, it started from some reloaded value. Let's say the counter counted down and it suddenly became 0. There is a comparator here which count and which checks whether it is 0 or not. If it is yes, then it will trigger an input. So there is a timer based interrupt that is possible, which you will be doing an exercise on. Of course, you will be not using a dedicated timer for that. You will be using the SysTick timer option for that, but concept remains same. So you give a reloaded value and check whether the counter is counting to 0. The moment it becomes 0, you trigger an interrupt, and you write an interrupt service routine corresponding to this interrupt vector, like the discussion that we had in the previous lecture. You write something there and it will execute that. So this is the concept of a free running clock. So moment it reaches 0, one more thing it will do, it reload the value. Okay, so it is like a free running clock. It counts from that value to 0, then again the value will be reloaded, it will become again 0, again it will be reloaded, and so on. It will be like a sawtooth, right? You can say, if a plot against time, it starts from something, it goes down like a ramp, then again it goes up, again it goes like a ramp, and so on. So it looks like a sawtooth. So that's a free running clock aspect. Other aspect I said is the compare aspect, right? So what do you mean by a compare? So interestingly, if you see this part, the top part, whatever here, let me draw it. So this part is already the free running part. Okay, so you added a sophisticated part which is here. Sophisticated part which is here, which is the compare part, and there is a register which is reused between compare and capture properties, but let's concentrate on compare. So you store a value here as a user. While you program, you write to a register which is a compare and capture register. So once you write that value, you will be always comparing that value with the timer, whatever the current counter output, and you see if they are equal or greater, or I would rather say if they are equal, it will actually trigger an input. Okay, if it is not equal, nothing will happen. It just keeps on down counting. And where is it used? Let's see a beautiful application. Okay, a typical PWM output generation. So let's say I put a value here, and that value is shown by the blue dotted or shaded line over here. That's a reference. And let's assume I'm putting this is an up counter mode. Okay, so you can this part, I put it as an up counter mode. It starts from 0 to some value. That value should be higher than the reference value or the value that you are putting over here. So, for example, it starts from 0, it counts all the way to that higher value here. Okay, so that higher value you can safely put in the reload value. So what I am actually saying is this reload value should be higher than this compare value that you're putting over here. Okay, now let's let's assume this curve. Okay, so let's ignore this blue shaded line for a moment. So if that blue shaded line is not there, it acts like a free running counter or free running mode. So you count from 0 to a certain value. Once reaches that value, all the way to 0 again. So it's like a sawtooth, it goes on. Now I'm putting some compare value here and enable this mode. So that means there is a compare line here. That is the value that I'm putting. So what happens is till that time, this counter value is always less than the compare value, nothing will happen. The moment they becomes equal, an interrupt is triggered. And my interrupt service routine will start something like this. So this is the output of the interrupt service routine, which is going to the PWM output. Okay, so I have to do it. There's no magic here. So I'll create, it was 0 before, so I will toggle that output to 1 or some high value. And then that value will remain high till the next interrupt comes. When will the next interrupt comes? The first interrupt is the value will increase and then it becomes equal. The first interrupt is triggered. Then it continues to increase. Then the values are not equal. So nothing will happen. So my interrupt service routine or whatever the value, the output will remain at 1. And then the counter value reaches its maximum value, the reload value. It starts suddenly a drop, right? It drops to 0. At that point, a brief instant maybe, that time again an interrupt will be triggered and you go to the interrupt service routine, you toggle the output, come to 0. And it gets keep on repeating. The beauty about this curve is actually you can use it to control the speed of a motor. So what does the speed of a motor depends upon? Let's say DC motor, to make it simple. The speed of a motor is directly proportional to the input voltage. So if you give some input like this, a DC motor will treat it as an average DC value, right? So the average value, if I take off this, will be this pink shaded line here. So it's a low value. Now let's say I lower this threshold to somewhere here. So I just want to draw it for you. Maybe it becomes messy. Excuse me for that. So this is a new reference line. Okay. So in that case, let me change the color. So let's say green. Okay. So this is the value where my new thing will go. And this is the value where the thing will go. So let's say I have the new curve, something like this. Okay. And then similarly here, sorry for my drawing skills. Okay. So the next pulse will be here. And then the third pulse will be, sorry, again. So you see the pulse width of the on time increase from this to this one. Similarly, all of them. So the average value, if I take, will be somewhere here. I'm just assuming. Okay. So your average value is increased, and then of course the speed of the motor will increase like that. So by just controlling the compare value here, okay, if I change the compare value, I can change the pulse width, and I can change the average DC value. I can change the speed of the motor. Please try it out. Beautiful application. I don't have any lab exercise on that, but nobody prevents you to try this out. Please try it out. It's very, very interesting, right? So moving on. So we talked about the free running mode. We talked about the capture mode. Sorry, comparison mode, where you create a what you call pulse width modulation. Now let's see the capture mode. Again, this value, this part remains the same. It's a free running mode. This is the new circuit for the capture mode. So again, you have to give some value to the capture register, and what happens actually is this timer counter, when it reaches that capture value, whatever polling that you are going to do, that will be captured. Okay. It will trigger an input, and you can actually say that you poll that input. Okay. Sorry if I confused you. So you store some capture value here. So that instant of time when the timer value equals to that value, an interrupt will be triggered. And then corresponding input will be polled during that time. This is an example. So everything will remain same. Okay. Except only thing is that the acting will be slightly different now. So that's a capture mode. Okay. You give a capture register value. Whenever the timer value is equal to that register value, your input will be polled. And you have to write the code. Okay, that is important aspect. So there's no magic here. You have to write the code. You have to write an interrupt service routine which will poll the particular input that you are interested in. Okay. This, for example, one application is the photodiode. The other one is the speed encoder. Okay, that's again photodiode based. If you want to measure the speed, you do a polling service. That's not really good, but this is a way to go about it. Now, how does it happen in our freedom board? That's a very important aspect, right? So if you go and see the timer, so let me just discard it. Okay, so let me just go back and see our reference manual. This is your Bible. Just go to the timer. There is a timer. Let's see that low power timer. Okay, so not this timer, right? This one. Low power timer is similar, but this is more generic module. So you go to there. You can go, just go down this, or I'm showing there, it is over here. If you go down, you will have the details of each one of them, the registers that you should be caring about, all the details are here. So now onwards, I will not spoon feed you. You just go and see, understand this by yourself. It's quite straightforward, it's quite easy to understand, but I will just explain to you this block diagram in this detail. Okay, as an engineer, you should actually be very well familiar with this block diagram. So let's go from top to bottom. So this is the place where you actually have capability to write to a register, clock mode. In fact, this is not an individual register. It will come in one of these registers. Okay, so it will be in the status and control. Okay, inside that, a field is actually clock mode, and based on the value that you give, it will select one of these options. So you will not select any clock. That is the default. Okay, so clock is disabled. I think by default it is disabled. So it will be some maybe 0, 0, 0, or maybe this is only 3 inputs, right? It will be 0, 0. So that when you select that by default, it will be disabled. So other option is you give that value so that the internal module clock will be selected. The other way is to select an external clock with some synchronizer circuit which is done for you. So three options which is given by this clock mode register. And then you have a prescaler option. So you can prescale this value as I was showing you in the previous slide. And there is a register where you can select 1, 2, 4, 8 up to 128. So you can divide your clock frequency by one of these values. That's again up to you. You write to the register, that's all you need. And the internal hardware is already done. That is again, I keep on reiterating, that is a beauty of microprocessor. It is a software controlled digital circuit. So you write to this register, it will select the appropriate clock. You write to this register, it will select the appropriate clock division or clock frequency division. And then another register here which will help you in selecting up and down mode of your counter. So you can make the counter counting up or counting down. Okay. So based on this clock frequency, every clock frequency either edge or level, I think that control also is there. It can be level triggered or edge triggered. You can actually make the counter count up or down based on this register. Is not it very beautiful? Yes, it is. So then these are the individual blocks. So many channels are there. So each channel output can be given to a certain port, for example, GPIO, for example. So this is mostly for the output side, the PWM, for example. So different channel options are there. You can actually go and see how many channels are there for our board. And this is the other side which is coming from the polling part. So you want to poll something, some channel, you can actually do that as well. So you connect that GPIO to this channel, it will poll that. Okay. So this is the poll, the capture option. This is the compare option. So that's what I'm saying. And then this counter will come and sit for this register. So for the capture mode, you basically whenever this counter, so whatever value you want to write, okay, so the counter counts, and then the capture register and the counter register is this register. So you write to that register some value. For the capture mode, if the value is, the counter increases, and if that value is equal to this value, the channel will be captured. That instant will be captured and will be an interrupt will also be triggered. On the comparison option, if the counter value is equal to this value, automatically the interrupt will be triggered, as well as the corresponding value or thing will be available for you at the output. So this, please go through the document. If I'm not understanding or if I'm going too fast, please go through that document. It clearly explains. And the only way to understand it or to get used to it is to do some exercise. So we will try to do that in the lab when you come back. So you will get well versed with that. And all these, whatever clock mode, up, down, timer overflow, interrupt enable, timer overflow, etc. all these registers, all these things are available in these memory map associated with the timer, and you can see the location. It is almost in that peripheral region. Okay, so this register is the status and control register, and then you have three timers: TPM 0, 1, and 2. If you go back and see in this document, this called, you can see it here. TPM 0, so first timer, second timer, and three timers are available. Certain channel values also. So let me just quickly go to one of these. So channel, you can see it over here. Okay. Okay, so many options are there. You see mode option, and then you see the options possible. Mode is a 15-bit or 16-bit rather, and you can actually see the options. Okay. Okay, so that concludes sort of a very short, crisp session on timers. Ideally, I would have combined the interrupt with timer. Even the lab exercise is done that way. But I thought I would like to explain this in some detail. And this concludes the lecture sessions for this week. Okay, so basically the week of 20th, you have 3 days, and I would suggest you to actually read it through 3 days, 3 lectures. And I will try to upload some of the lab exercises also soon. And as I said, if you have any questions, please put your questions in the discussion forum, or you can write down your question, and maybe we'll try to address that during one of the live sessions that we have. Hope you enjoyed the lecture, and keep coming back for the subsequent lectures. Thank you.